Welcome to the tutorial on A2 broken authentication and session management. Now first, let's start with our definition for this particular category. Application functions related to authentication and session management are often not implemented correctly. This allows the attacker to compromise passwords, keys, session tokens, or exploit other implementation flaws for the main goal of assuming other users' identities. Security weakness. Developers frequently build custom authentication and session management schemes, but building these correctly is hard. As a result, these custom schemes frequently have flaws in areas such as logout, password management, timeouts, remember me, secret question, account update, etc. Finding such flaws can sometimes be difficult as each implementation is unique. Now let's take a look at some of the possible attacks in this area. Session fixation is certainly one of them. Now session fixation is where an attacker is fixated on a particular session, token or a cookie. It's usually revolving around cookie security, and I have some examples. Let's see them. First example is where cookie setting actually remains the same after login. So initially when you go to a website, more than likely there will be some sort of initial cookie before you actually authenticate it on the website. Sometimes this is done to keep track of things that you have looked at, or maybe there is a card that is available, a shopping cart, and so. Once you log in, however, that session ID or cookie is supposed to change, otherwise you can fall prey to session fixation. If the cookie were to remain the same, an attacker could get that cookie and then assume your identity. Now another example where session fixation could occur is if the cookie value is predictable. So if an attacker is able to determine what the next numeric number is going to be, then that's a very attack or a session ID to create on their own. Another example is where the cookie value is unencrypted, and so the username and password is just shown in clear text. Now this is usually the result of not setting the secure flag, which is generally something that can be either done programmatically or through the web server setting. Now, also in this category, there is a lot about password management. One of the attacks around password management is brute force attacks. Now, brute force attacks generally can start with some sort of username enumeration. So, this enumeration is basically going to be listing of all valid accounts. Why start with some random account names if you can go ahead and enumerate those accounts that are valid? It saves the attacker a lot of time. Now, the way that username enumeration can possibly be done is through the use of some verbose error messages. So if an error message gives too much information, or even if it's not an error message, say it's a success message of some type, if it gives too much information, that can be a clue that attacker could possibly enumerate information from. Information that will be stored in the database should not be available to them. Another way that brute force attacks can occur is if there is a very weak password policy or no password policy at all. Now, password policies are generally those things where a website will say that you have to have a minimum of 8 characters or numbers, 2 special characters, and things like that. Included in password policy should be things like no dictionary words or password aging setup, or not allowed to use previous password up to last 10 times. And of course, the main issue with the real-time brute force attacks is that there is no account logout. So generally, on a lot of websites now we see there is usually 3 or 4 attempts threshold, and once you reach that threshold, the account is locked. And yet another area of brute force attack would be insecure password storage. So in general, password must be hashed. Now hashing functions are irreversible. In another word, they don't actually ever get decrypted, and so they should be encrypted or hashed inside of the database at all times. Now, when the passwords are not hashed, when they are in clear text, then they can be easily susceptible to the dictionary attacks, provided all the other things remain as well that we have just discussed. In addition, sometimes companies will hash passwords, however, they will not use what called salt. Now salt actually is a piece of randomness that is placed into the hashing function algorithm to provide strength to the hashed password. Passwords that are hashed but do not have salt are susceptible to rainbow table attacks, which essentially are dictionary words but computed with hashing functions that don't use the salts. So let's take a look at our first example. Here we have some sort of broken authentication session management design flaw. So in this example, you can see that I have Verbsuit actually capturing a cookie at the login page. Now this particular session ID that is being used as a PHP session ID. So all I did was I made sure that I was not logged into the application. I went to the login page and I actually did a refresh. I captured the cookie that is set on the response, and then I went ahead and logged in. And after the login, you can take a look at the cookie again. Now, when the cookie has the same exact value even after login, this is going to be session fixation vulnerability. So basically, that means an attacker could get hold of that cookie and obviously use the same cookie to masquerade as the legitimate authenticated user. Now I will discuss about a case study on Gmail cookie stealing and hijacking. It actually corresponds very well to the slide that we just looked at. This is the case where Gmail basically had encryption only on the login screen. This takes us back to 2011. So what used to happen is when you come to login screen, Gmail would switch from HTTP to HTTPS. But after you log in, all of your mail and your cookie would be exposed in clear text and be exposed back to HTTP. And the only way you can undo this is to go to advanced setting at that time and turn on HTTPS to yourself, which of course most users probably didn't know how to do. And this article basically goes through a lot of session hijacking and session fixation type vulnerabilities and exploitation that occurred because of that flaw. Now for our third secure coding standard example, this is in Java programming language, but of course the same principle can be applied to any programming language. So the rule states never hardcode sensitive information. Now this particular example that we have, the username and password actually of the account that is used by the application to connect with the database. And the information is actually hard coded right into the strings within the code itself. Now there are a lot of reasons why this is problematic. First of all, this means that you are using the same username and password in every single environment, which is the first problem. The second problem is that it becomes part of your binary, which means that this information is going to be more easy to attack. Should your binaries be lifted by the attackers and decompiled or even run through debuggers to be read in memory? Another problem is that when it comes to external cloud storage areas, this has become something that is commonly done. The main reason why is because there is sort of disjointed relation when you have this external vendor, this third party that provides this cloud storage, and so getting an account to that just seems sort of distant from that particular custom code that you're working on. And even more so, we are finding that this is being exploited, basically having developers connecting out into the cloud from their private data centers. Now the compliant version of this is to of course externalize applications database account information. Now when I say externalize, I mean either put it in the configuration file or put it in the database, ensuring that either one of those options also provide encryption of that password. So if you are using Java, you can use, for example, the JSEC library offers a very good utility for the name value pairs that can be encrypted. And if you're going to store it in the database, you need to ensure that it is encrypted inside of the database. And if it's Oracle, there are DBMS crypto libraries and settings that can be done in order to ensure that when the information is read in the memory in transit, yes, it's going to be decrypted, but it obviously has to be in order to make sure the connection. But at least your transient time of decryption should be minimized as opposed to the hard coding inside of your source code.